Hello and welcome to Mathematics Illuminated, where I shed light on any and all math topics from simple to advanced in a way that is easy to understand and interesting to learn. Please subscribe to my channel as I continue to post more videos and comment below on videos you'd like to see in the future. This is part 5 of a series I have on complex numbers, and I'll leave a link to parts 1 through 4 in the description if you haven't seen them yet and would like to check them out. In this video, I'll be going over the natural logarithm function and how it is used with complex numbers. I'll answer the questions: what is the natural logarithm? What are its properties? How does the natural logarithm work on the complex number plane? What is the principal branch of the natural logarithm? And how do you take the natural logarithm of a complex number? The way the natural logarithm is defined is by the equation e to the natural log x equals x, where e is Euler's number, approximately equal to 2.71828. I'll leave a link to my video on Euler's number in the description if you want to check it out. A common way to think about the natural logarithm, if you're familiar with base 10 logarithms, is that it is just a logarithm with a base of e. With this definition, we can derive particular values of the natural logarithm. According to the definition, e to the natural log of 1 equals 1, and we know that e to the 0 power equals 1, and so we can see that the natural logarithm of 1 is 0. Additionally, according to the definition, we see that e to the natural log of e is e, and we know that e to the 1 power is e, and so the natural log of e is 1. Most values cannot be as easily simplified, however, and must just be written in terms of the function. For example, the natural log of 2 cannot be simplified and is approximately equal to 0.69315. This is the graph of the function, and you can see that as the value inside the natural logarithm gets closer to 0, the value of the natural logarithm gets closer to negative infinity, and so we say that the natural logarithm of 0 is undefined. In part 4, I went over Euler's identity, which states that e to the pi I equals negative 1. This helps in showing us that the natural logarithm of negative 1 is equal to pi I, since that is the number that e must be raised to in order to get negative 1. There is an issue with defining the natural logarithm just as a solution to the equation, though. As it turns out, given the equation e to the x power equals y, x has an infinite amount of values on the complex number plane, being represented here as the natural log of y plus 2 pi ni, where n can be any integer. Recall, integers are numbers like 1, 2, 3, etc., 0, or negative 1, negative 2, negative 3, etc. We can see why there's an infinite amount of solutions when we plug it in as a solution. Using exponential rules, we can split the exponent, and then we can use Euler's formula, discussed in part 4, to expand e to the 2 pi ni as cosine 2 pi n plus sine 2 pi ni. Evaluating these angles in radians shows that for any integer n, the angle will be at this point. And then defining the cosine and sine functions as x and y coordinates in the unit circle, we see that cosine 2 pi n equals 1 and sine 2 pi n equals 0 for any number n. And so this expression equals 1 plus 0i, which is just 1. And multiplying by 1 in the previous expression would just leave you with e to the natural log of y, which gives us our desired result y. Expanding on this idea of it having an infinite amount of solutions, we can use this to see that solving the equation e to the x equals negative 1 for x gives that x is equal to pi I, 3 pi I, 5 pi I, and so on. It additionally could be equal to the negative versions of any of these. And this, of course, creates a problem. The natural logarithm is supposed to be a function, and functions are only meant to give one result, not an infinite amount. And so that's why we use something called the principal branch of the natural logarithm. Allow me to explain. The real and imaginary parts of a complex number can be expressed using the expressions re and im, and so the real part of 5 plus 3i is going to be 5, and the imaginary part is going to be 3. Well, as it turns out, when treating the natural logarithm properly like a function using the principal branch, the imaginary part has to be between negative pi non-inclusive and pi inclusive. And recall when we showed all the solutions to the equation e to the x equals negative 1, only one of these solutions has the imaginary part between this range, and it is pi I, because the imaginary part of pi I would just be pi. And so the natural logarithm of negative 1 is just equal to pi I. If you're confused why this is called the principal branch and not just the only branch, it is because some define the natural logarithm using an infinite amount of solutions, but that method gets hard to keep track of and fails to allow the natural logarithm to be a function. And so it is best to define it as just the principal branch, which is the branch where the imaginary part is between the desired range. Using another example, here we can see the equation e to the x equals I and the infinite amount of solutions for x. Despite all these solutions, though, the exact natural logarithm of I is pi over 2I, because that is the only solution where the imaginary part falls between the correct range. The next topic I'm going to get into is this property of natural logarithms that is commonly cited. However, this doesn't always work for all values on the complex number plane, and allow me to explain why. What I'll do to explain why is go about proving it. Here we have the definition of the natural logarithm, which never fails to be true, that e the natural log of x is x. Then what we can do is take the natural logarithm of both sides. Then let's call z equal to natural log of x. Substituting z into our equation gives that the natural log of e to the z equals z, and that is how we get our rule. So why doesn't this always work? Well, remember, the natural logarithm has to have an imaginary part between the ranges of negative pi non-inclusive and pi inclusive, and that is what we called our z. And so the equation natural log e to the z equals z only works if the imaginary part of z is between the desired range. So it doesn't always work, but that doesn't mean it is useless. For example, in the complex number 1 plus 2i, the imaginary part is 2, which is between the desired range, and so the natural log of e to the 1 plus 2i is equal to 1 plus 2i. With the complex number 3 plus 5i, however, the imaginary part 5 is not between the desired range, and so the natural log of e to the 3 plus 5i fails to be equal to 3 plus 5i. Using the natural logarithm with complex numbers leads one to wonder, can you take the natural logarithm of just any complex number, x plus yi? Well, fortunately, this is very possible. First, what you need to do is rewrite your complex number x plus yi in polar form, which I discussed how to do in parts 3 and 4 of this complex number series. Recall here that r is going to be the radius of the complex number, which is a positive real number, and zeta here is going to be the angle or argument of the complex number, which is between the ranges of negative pi non-inclusive and pi inclusive. Then what you can do is employ the common rule natural log AB equals natural log A plus natural log B, which you may recall is a general rule for logarithms, to solve this. Though that rule does not work for all complex numbers, and I'll explain why in a bit. For now, though, we can use this to expand the natural logarithm of our complex number in polar form as the natural logarithm of the radius plus the natural logarithm of e to the zeta I. And we already said that our angle theta is going to be between the range of negative pi non-inclusive and pi inclusive, which is exactly the conditions we need to employ the rule here for the exponent acting as the imaginary part, allowing us to write this as simply zeta I. And so the natural logarithm of any complex number is going to be the natural logarithm of the radius plus the angle or argument multiplied by I. And so let's try this with a particular example. Finding the radius using the method discussed in part 3, we can see that it is equal to the square root of 13. And noticing our complex number is going to be in the fourth quadrant, we can write the angle using the methods in part 3 as the negative arctangent of 3 over 2. And so we now have our answer. Though recall another rule for natural logarithms that you might recall is a rule for logarithms in general, where we can take the square root out and represent it as multiplying the natural logarithm by a half. And so we have our final answer. The natural logarithm of 2 minus 3i is half of the natural logarithm of 13 minus the arctangent of 3 over 2i. Pretty interesting, right? Now what I'll do is explain a bit about why natural log AB cannot always be expanded as natural log A plus natural log B for all complex numbers. If imagining them as complex numbers, you rewrite them each in polar form, here distinguishing between radii and angles by labeling them using 1 and 2. You find that you multiply the radii and add the angles together in the exponent. And employing the same thing as before expands it like this. But notice that this expression could possibly be outside the desired range, and so cannot immediately be simplified. If hypothetically it was in the desired range, though, we could expand it like so, and so the rule would hold up that it would be expanded as natural log A plus natural log B, which is expressed here using how they would be expanded using polar form. But since we don't automatically know whether or not the angles add together to create an angle within the desired range, the rule does not always work. Allow me to give an example of this. The natural logarithm of -1 multiplied by itself would create the natural logarithm of 1, since -1 multiplied by itself is 1, and the natural logarithm of 1 is 0, so this whole expression simplifies to 0. But if we tried employing the rule here, we would get that the natural logarithm of -1 added to itself would be pi I plus pi I, which is 2 pi I, not equal to 0. And so the correct answer is 0, and the rule does not work, because the angles do not add to a number within the desired range. If you tried taking the natural logarithm of I multiplied by I, however, you would get that it equals the natural logarithm of -1, which is pi I. If you tried using the rule, you'd get natural log I plus natural log I, which is pi over 2I plus pi over 2I, which produces the exact same result, because the angles do add to get to a number in the desired range. And so, sometimes this rule works and sometimes it doesn't. And so, to summarize this video, e to the natural log x equals x by definition, but the imaginary part of natural log x is always between the range of negative pi non-inclusive and pi inclusive. And the natural logarithm of any complex number is going to be the natural logarithm of the radius plus the angle multiplied by I. And that brings me to the end of this video. Please subscribe to my channel, like this video, and keep an eye out for future videos. Farewell for now.